Hello, in this presentation I will discuss different ways to summarize and visualize data. Specifically, I will explain the differences between the different types of variables and describe several methods to graphically summarize and visualize data based on the type of variable that we work with and the purpose of our data analytic project. I will talk about pie charts, bar charts, stem plots, histograms, box plots, time plots, scatter plots, and geographic plots. As illustrated in this diagram, variables can be of different types. Some variables are called quantitative because they take numerical values and can be used for computations like test scores, for instance. Quantitative variables can be of different kinds though. Some of them are called discrete because they can only take specific values or rounded values like integers. A discrete variable is a quantitative variable that has a finite number of possible values or a countable number of values. An example of a discrete quantitative variable is IQ scores. They range from 0 to say 150 and can only be integers. A continuous variable is a quantitative variable that has an infinite number of possible values in between integers. Such variables are weight, height, speed, and so on. They can have an infinite number of decimals. Continuous variables can be divided into another two categories, interval variables and ratio variables. When variables are on a ratio scale, the value 0 represents nothing or the absolute absence of an entity. For instance, an object of height 0 or weight 0 does not even exist. For variables that are measured on an interval scale, the value 0 is simply the beginning of an interval and does not indicate the absence of that entity. For instance, the temperature 0 is simply a point from which we begin the scale, but there are temperatures that are at or below the 0 point regardless of what temperature scale we use. Another type of variable is the categorical type. These variables are also called nominal and have a certain number of categories, but the categories cannot be ranked in any way. For instance, gender is such a variable, or the individual's names. These do not have numerical values and cannot be used in computations. However, just for practical reasons, when entering data in the computer, the different categories sometimes receive a numerical code like 0 for females and 1 for males. But these codes do not really have a numerical meaning per se. They are just replacing the words to facilitate the manipulation of the datasets. Ordinal variables are similar to categorical variables because they also have a certain number of categories. But there is an important distinction between them. The categories here can be ranked. They have an intrinsic order. For instance, a test may have only two outcomes, pass or fail. Pass is definitely superior to fail, so even though we have only two categories, they can be ranked. Another example are survey responses. When responses to survey items are provided on a Likert scale, we can have, say, four categories: strongly agree, agree, disagree, and strongly disagree. These categories can definitely be ordered or numbered from 1 to 4 based on respondents' level of agreement. Our goal when using graphs is to illustrate the distribution of each variable, which means that we want to show the values that the variable takes across the individuals in the sample. We want to see what is the range of values and what values or categories occur more often than others. Now, the type of graphical illustration that we should use depends on the type of variable that we're working with. For categorical variables, we can use pie charts or bar graphs, whereas for quantitative variables, we can use different kinds of graphs such as histograms, box plots, or stem plots. A pie chart shows the distribution of a categorical variable. It illustrates all the categories and gives the count or percentage of individuals who fall into each category. This example illustrates the racial distribution of the student body at the University of West Georgia. This is real data, and each slice of the pie indicates the percentage that corresponds to each subgroup. Pie charts can be used only when all the categories put together form a whole, so all the percentages add up to 100%, and therefore the categories are mutually exclusive and each individual can only belong to one subgroup. Bar graphs are also used with categorical data, but the different categories do not necessarily form a whole, and individuals may be included in more than one category. For instance, this bar chart shows how teachers responded to the question, "What can be done to improve instruction in our school?" This is a type of question where respondents can check all the responses that apply, so one individual may check more than one box. Therefore, the percentages represented by each column do not add up to 100%, and adding these percentages does not make much sense. The distribution of a quantitative variable tells us what values the variable takes and how often it takes those values. This is an example of a histogram and it illustrates the distribution of students' weight. The first step in producing a histogram is to divide the range of possible values into equal intervals. Statistical software does this automatically, but you can change these intervals if you want. In this case, the values of the weight variable range between 100 and 280, and the intervals are set at 20 pounds. So the first column represents the number of students who have between 100 and 120 pounds. The second represents the number of students who weigh between 120 and 140 pounds, and so on. When interpreting a histogram in any other graph, we try to describe an overall pattern and also identify any striking deviations from that pattern. For instance, here we see that the majority of students weigh between 100 and 220 pounds. The distribution across different categories in this range is approximately uniform, except for the 120-140 category and the 180-200 category. So these are much more frequent among the students in the sample. We also notice that we have an outlier, one individual who is located in the 260-280 category. An outlier is an individual who falls outside of the overall pattern or records extreme values. Stem plots are also considered graphical representations, but they use numbers to show how variables are distributed. A stem plot looks like a histogram that is turned on end. This example shows the distribution of a student IQs. The first column, labeled STEM, shows the first one or two digits of the IQ score, the tens digit and the hundred digit. And the columns labeled leaves include the last digit or the ones of the IQ scores. For instance, in the first row, we have a stem of 3, which represents the tens digit, and a leaf of 8, which represents the ones. Together, they make an IQ of 38. In the third row, we have a stem of 5 and 2 leaves, 1 and 3. This means that one student has an IQ score of 51 and another student has a score of 53. For each stem, the number of leaves shows the number of students who have scores at that level. We only have one student at the 30 level, one in the 40 level, two at the 50 level, three at the 60 level, five at the 70 level, and so on. We can tell from this graph that most students have the IQ at the 100 level. The IQ average in the population is 100, so it makes sense to have the most students located somewhere around this value. Values that are very low or very high are less frequent. We only have two scores at the 130 level, 132 and 135. And we have an outlier with a very high IQ score of 152. Box plots or box and whisker plots are another way to illustrate the distribution of a quantitative variable. The middle line that you see in the box represents the median or the middle point of the distribution. The lower whisker or the left side whisker begins with the minimum value and extends until the first quartile. Therefore, this line represents the first or the lowest 25% of the values. The box begins at the first quartile and ends at the third quartile, and therefore includes the next 50% of the values in the dataset. The values in the box are also referred to as the interquartile range, and as I mentioned, they represent the middle 50% of the values. The upper whisker represents the top 25% of the values. For instance, in this example, we have three box plots showing the distribution of student scores on a post-test. These distributions are represented separately by socioeconomic status. The dots that we see outside of the whiskers are outliers or extreme observations. When data have a relatively normal distribution, the median line is in the middle of the box and the whiskers are approximately equal in length, like the box plot on the right side that shows the distribution of scores among middle class individuals. When data are skewed, the box and whisker plot is not symmetrical like the one we have for individuals with low socioeconomic status. In our example, the middle class students have a symmetrical and more spread distribution of scores. However, the low SES student scores are located mostly at the lower end, with a few outliers at the higher end. In contrast, the distribution of scores for high SES students is located at the higher end, with a few outliers at the lower end. A time plot is a graphical representation of how a certain variable changes over time. In this case, we collect data several times, not just once, and we record the values of the same variable at different points in time. For instance, this graph represents the changes in college tuition across years for public and private universities. Time is always represented on the x-axis, which is the horizontal axis, and the y or the vertical axis represents the values that the variable takes over time. Data points are connected with a line to better illustrate the trends over time. In this case, we can see that tuition has increased over time for both public and private schools, but the rate of increase is much higher for private schools after the 1980s. A scatter plot, also known as a scatter chart or scatter graph, uses dots to represent values for two different numeric variables. Each dot represents one individual. Scatter plots are used to examine the relationship between two quantitative variables. One variable, which is typically considered a predictor, is placed on the x-axis, whereas the other variable, which is considered the outcome or the response variable, is placed on the y or the vertical axis. Scatter plots help us visually examine the distribution of the two variables in relation to each other and get a general idea about the strength, the shape, and the direction of the relationship. The relationship is strong when the dots tend to describe a line. The relationship is weaker when the individual data points are further away from a line and look more spread like a cloud. A relationship is linear when the shape clearly describes either an upward or a downward trend. Linear relationships can be positive when the line describes an upward trend, or negative when the line describes a downward trend. A positive relationship means that as one variable increases, the other variable also increases, like we see in example B. An example of such a relationship is the relationship between educational level, for instance, and income. Most often, an increase in the level of education is associated with an increase in income. In a negative relationship, like we see in example C, as one variable increases, the other variable decreases. For instance, we often see that higher levels of poverty are associated with lower levels of educational attainment. We also have an example of a curvilinear relationship in plot A. A curvilinear relationship can be observed when there is both an upward trend and a downward trend, and the shape describes a curve. This can often describe the relationship between age and physical or mental abilities. We first see an improvement with age, and then later in life, a decline with age. It is very important to remember that this is just a graphical representation. While it is very helpful, there are more precise ways to measure relationships among variables using statistical procedures such as correlation coefficients, regression analysis, path analysis, structure equation modeling, and so on. The visual inspection of the data is just the first step of the process. Another important aspect to remember is that a scatter plot indicates the mere association between two variables and is not evidence of a causal or predictive relationship. Again, more complex data analysis procedures are needed to support such claims. Here is an example of a scatter plot showing the relationship between scores on a pretest and scores on a post-test. This plot shows a linear, positive, and quite strong relationship between the two variables. We can see that, with a few exceptions, individuals who scored high on the pretest also scored high on the post-test, and vice versa, and the dots describe an ascending line. Although we say that scatter plots show the relationship between two variables, in this case the relationship between pretest and post-test scores, this type of visualization can convey other types of information as well. For instance, we can use different colors or different types of markers to represent the values of a categorical variable. In this example, the colors represent student socioeconomic status. We can see that the color blue, which represents a higher socioeconomic status, is more prevalent among individuals with higher scores, whereas the color red, which represents lower socioeconomic status, is more prevalent among individuals with lower test scores. In this graph, we also use the size of each data point to reflect the values of another variable, which is the number of hours that students spent studying each day. We can easily see that, for the most part, the smaller dots are located on the left side, indicating that individuals with lower scores tend to spend less time studying each day. At the same time, we can see that most of the larger dots are located in the upper right corner, indicating that individuals with higher scores tend to spend more hours per day studying. Therefore, scatter plots can be used to visually describe the relationship between two quantitative variables, but can also represent information from one or more categorical variables. Geographical plotting is a method of displaying data on a map, which can be at a global scale as well as for states or regions of a country, often in a colorful manner. Geographical plotting or geoplots play a significant role in data analytics and visualization. They are commonly used while building dashboards to present widespread data. Here is an example of a geographical representation of the highest degree of educational attainment in the United States by state and by county. Color is used here to indicate the prevalence of different levels of educational attainment, where dark purple represents mostly less than a high school education and dark green indicates the prevalence of individuals with a bachelor's degree or more. Often, such graphical representations are interactive, and users can select criteria for summarizing or displaying the data, or can hover over some of the areas to see more information. For instance, in this type of graph, a user may change the range of years for which the data are displayed, or may hover over a particular state to see the actual frequency distribution of academic degrees in the region. Geographic plots are not just aesthetically pleasing and interesting, but they are also important in data analytics because they provide context for our data values. In this presentation, I explained the differences between different types of variables and described several ways to graphically summarize and visualize data based on the type of variable that we work with and the purpose of the analysis. Specifically, I described pie charts, bar charts, stem plots, histograms, box plots, time plots, scatter plots, and geographic plots.